All right. Well, welcome back, folks. Let's pick up what we left off with yesterday. So we left off yesterday talking about these molecular orbitals. We talked about what they are, and we talked about how they formed. Okay. We talked about how these molecular orbitals are essentially then the atomic orbitals coming together to form these new molecular orbitals that represent the electron distribution around a molecule rather than electron distribution around the atom, which are the atomic orbitals. Okay, so essentially then these atomic orbitals, which are waves, wave functions that we talked about, what they do is they come together and they will interact with one another either in a constructive manner or in a destructive manner. Okay, so make sure you understand then, an example we gave was two hydrogens coming together. I chose hydrogen because hydrogen is the simplest atom. You have one electron in the 1s orbital, and it's easy to understand then that when you take those two orbitals, the 1s orbital from the from one hydrogen atom and the 1s orbital from a second hydrogen atom, these can be viewed as standing waves. You remember we talked about the de Broglie model of the atom, and so these electrons then are standing waves, which corresponds to the idea then that these electrons are also wave functions according to Schrodinger's equation. And so you take these waves and then you make them interact with one another. And when these waves interact with one another, they will interact with each other either in a constructive manner, which means that the waves add together, or a destructive manner, which the waves then cancel each other out. So we saw then when the two 1s orbitals here, when they interact in a constructive manner, you get a bonding molecular orbital. We refer to this then as the bonding molecular orbital. And you also have the antibody molecular orbital. And if you notice here, with the bonding electron orbital, molecular orbital, I'm sorry, you see then that you have a high area of electron density between the two nuclei, whereas with the anti-bonding, you have a node that runs right down the middle, which means then you have no electron density in that region, which means then when you have a anti-bonding molecular orbital, you do not have electron density between the two atoms. And again, for a bond to form, you have to have those electrons sitting between those two atoms, and this is the one aspect of molecular orbital theory that corresponds to the localized electron model. Okay, so I'll mention that again in just a few moments. Okay? All right, so here we have it, and we see then that when the electrons, when the hydrogen atoms are separated, okay, they are at a higher energy level. So this particular diagram here, the energy diagram shows us then that when the hydrogen atoms are separate from one another, the electrons sit at a certain energy level. Then as they get close, and when the bond forms, and remember, we talked about the molecular orbital here as being the bonding molecular orbital. This is a pro-bonding state, which means then the electrons then are in a lower energy state, and therefore then they are more stable. And so this interaction, which involves the two electrons between the two hydrogen atoms, that then is your covalent bond. Okay. The anti-bonding state here, which is what we saw here with the destructive, with the molecular orbitals here, these are higher in energy. This particular orbital is much higher in energy than the atoms separated. So these electrons then would prefer not to go up here. They would rather go into the lower energy state. And we saw this particular diagram. And so we said then that that's going to be the bonding molecular orbital versus the antibody molecular orbital. And we saw how this happened. So the diagram that I was trying to draw for you yesterday, make sure you keep this in mind, that this represents here the two hydrogen atoms in their separate state. They are at a higher energy level. Remember, this is the diagram we saw from chapter 8. So please make sure you look back at that, okay? Which plots for us then, this graph here plots for us potential energy, which is energy, versus internuclear distance, which means how far they are away from each other. So these two atoms are separated. They are far away from one another, and that each one of this corresponds to this state right here. Okay. Then, as they start moving closer and closer together, they decrease that internuclear distance so that we get to a point where we're about 0.074 angstroms away from one another, or I'm sorry, nanometers away from one another. Then you see then that the energy diagram here dips. The energy diagram dips right here. This represents then the pro-bonding state, where the electrons, where the pro-bonding state, where the electrons now, these two electrons, which were separate, remember you have an electron here in the 1s orbital, electron here in the 1s orbital, here you have then electrons sitting in the bonding, when you have the pro-bonding state, this represents then the bonding electrons falling into the bonding molecular orbital. So you can imagine then these two atoms, as they get closer and closer together, they're 1s orbitals. We start out with 1s orbital here, 1s orbital here. As they start getting closer and closer together, the two 1s orbitals, they start to interact with one another in a constructive and a destructive way. And once they get to this point here, then you have then the molecular orbitals forming, and that molecular orbitals where those two electrons end up occupying most of the time. Okay? And so that's what I wanted you to get from this, and that's what I want you to get from this, is that we can relate this particular energy diagram to what we see here in terms of the molecular orbitals that are bonding and molecular orbital is antibonding. And like I said, then this molecular orbital theory allows us to explain then the energetics, why this particular interaction even occurs, which we do not get with the localized electron model. Okay? All right, very good. So let's go ahead and let's proceed with this, and let's see where we come with. Okay? So remember what we have here then is we are saying then that these these orbitals here, these two orbitals represents the distribution of the electrons within a molecule. And so this represents then the favorable state, and this represents an unfavorable state. Okay? And so the way that these molecular orbitals behave is or the way that we can see them behaving is very similar to the way then that the atomic orbitals behave. And so it's that we can use the same basic ideas that we use for understanding atomic orbitals and how electrons fill atomic orbitals with how they fill these molecular orbitals as well. Okay, so now with that said, then if you notice here, then, and I pointed this out already, if this represents the hydrogen nucleus of one of the hydrogens, and this represents the nucleus of a second hydrogen, this area here represents an area of high density, high electron density, and therefore then the probability of finding electrons in this region here becomes much higher, which again corresponds then to the localized electron model, which remember told us then that the electrons sit between two atoms. And here we have it. Here, if the electrons fall into the bonding molecular orbital, we find then that the electron density is going to be greatest between the two atoms, which then corresponds then to the localized electron model and what it predicted. Okay, all right. Okay, so with that said, then we can actually label. If you notice here, we can actually use labels that are going to be very similar. Labels for the molecular orbitals. And so there are two labels here that I want to draw to your attention here, and that's this label here, which is sigma 1s and sigma 1s star. Okay, now the sigma here, it represents sigma, and I want to address this point to you really quickly, and that is, when we have the sigma interaction, this is also similar to the sigma interaction because there is a line of symmetry that you can draw through the both of those molecular orbitals, both meaning the bonding molecular orbital and the anti-bonding molecular orbital here. So remember, this is the bonding, and this represents the non-bonding orbitals. Okay, so that's what we have here. Okay. We refer to these as sigma molecular orbitals. So these are sigma molecular orbitals. So both of these are sigma. So we refer to this as sigma non-bonding. And this is the sigma bonding. And why is the sigma? Well, remember, with the sigma, and I'm just going to draw the sigma bond, and that's going to be the hydrogen A and hydrogen B right here. Okay. There is a line of symmetry very similar to what we talked about when we talked about the sigma bonding interaction with hybrid orbitals, but you can draw a line of symmetry, a straight line through this interaction here, and therefore then you can split it in half. That represents then a sigma interaction, and that's why we refer to this then as sigma, and we give it the letter sigma. Now the 1s here then represents then the atomic orbital. So this is the sigma molecular orbital, sigma bonding molecular orbital, and this is the sigma non-bonding or anti-bonding molecular orbital. And so that's what we refer to that as well. Okay, so with that said, then the 1s then represents the atomic orbitals that go into forming these two molecular orbitals. Okay, so with that said, then when we label the molecular orbitals, we label it with the type of molecular orbital it is, the way that it lines up with the sigma. Okay, we indicate then the atomic orbitals from which these molecular orbitals form. And then finally, then we introduce then this star here, okay? And this star here represents then higher energy. That represents then the antibody. That little asterisk represents then the antibody character of this molecular orbital. And if you notice then, when there's going to be a conservation of orbitals here, okay, and so you want to make sure that you keep that in mind. You can have a conservation of orbitals here, so that when you have two molecular orbitals forming, they form from two atomic orbitals. Okay, all right. So that's what we see down here, and I want to highlight that point for you. Okay, so that means then the number of molecular orbitals will always be the same as the number of atomic orbitals. That means then we have orbital conservation. What does that mean? That means then, if we take a look at this, okay, that when you have for the sigma 1s orbitals, we have then 1s orbital from one atom, okay, and this is the hydrogen atom, one, sorry. And we take that and combine it with, we combine that with the 1s orbital from a second atom, 1s orbital from atom B, okay, and this would be two hydrogen atoms. We get then two molecular orbitals. We get a sigma 1s and a sigma 1s star, which is bonding and non-bonding. We start out with two atomic orbitals. These are atomic orbitals. We end up with two molecular orbitals. Okay, so conservation here occurs, molecular orbitals. And so that's what we mean then by orbitals being conserved. Okay? And so, like I said, we can go ahead and we label. So we can label this as exactly the same way. Okay, and so we saw then that with the hydrogen molecule, there are two electrons that go into forming the bond here in this interaction that holds this molecule together. Both electrons fall into the sigma molecular orbital. This is no star, so this is the sigma bonding molecular orbital that forms from the 1s atomic orbital, and both electrons then fall into that particular molecular orbital. And so this is the electron configuration, if we want to write that. That's how we write the electron configuration for the hydrogen molecule, okay? All right, just one quick last note here, folks. Make sure you keep in mind that this is what's happening here is very similar to what happened with the hybrid orbitals, with hybridization, which was the localized electron model. Because remember, with, for example, sp3 hybrid orbitals, the way that those formed is that we took one s orbital from an atom, we combined it together with all three of the p orbitals, so we start to form then 4 sp3 hybrid orbitals. We start out with 4 atomic orbitals over here. So this is atomic orbitals. So we start out with 4 atomic orbitals, we end up with 4 hybrid orbitals. Okay, so what's happening here, up here with the molecular orbitals is very similar to what we talked about when we talked about the hybrid orbitals and the conservation there, okay? All right. Very good. So let's go ahead then, and let's continue on. Let me go ahead and clear this out. Okay, let's go ahead and use what we know then to ask this question. We saw then how the hydrogen molecule formed. We know then that the hydrogen molecule can form, that H2 can form because two electrons from the separate atoms come together, they drop down to a low energy level. So we know this molecule exists. We know then that the bond that between them, if we draw the Lewis dot structure, that bond between them exists as a result of two electrons falling into the sigma bonding molecular orbital. So this bond here is a sigma molecular orbital in which the two electrons are coming from the 1s orbitals of each hydrogen. Okay, so we know this molecule exists. We know that has to exist. The question then, could this molecule exist? Let's do a hypothetical molecule here where we have the hydrogen molecule as an anion. Okay, so let's take a look at how that could form. If it does form, let's take a look at how that does form. Okay, well, for this to form, then you can imagine then we would have to take a hydrogen, take a hydrogen atom. Okay, so hydrogen atom with one electron in its 1s orbital, and we'll call this hydrogen A again. And we're going to have to bring that close together with a hydrogen that is the hydride anion, which is H2. Okay? And that's going to be 2 electrons in the 1s orbital. Okay? And so these would have to come together. Okay? These would have to come together. And as they come together, they will form then this particular molecule here. Okay. Let's go ahead then and let's draw the, let's lay out the energetics for this. Okay, let's lay out the energetics for this and see what happens. Okay. Okay. So basically we'll be combining together three molecules, I'm sorry, three electrons. Okay, so we have to account for all three when they get together. And so when we look at the energy diagram here, let's see if that holds true. Okay. All right. So we have then, and I'm sorry, let me go ahead and do this here. Okay. Okay. So here it is. Here is the hydride. This is, whoops, sorry. Okay. Here's your hydride. So this is the hydride anion right here, or the hydrogen anion, not hydride. So there's a hydrogen anion with the 2 electrons in its 1s orbital. Okay, so there's the 1s. Here is the hydrogen ion with its 1 electron in the 1s orbital. So both these electrons here and this 1 electron here in the 1s orbital. Well, like we said, when you take so you got 2 1s orbitals. So you have a 1s orbital here and 1s orbital here. They're going to come together. And when they do, they're going to form 2 molecular orbitals. Here you have your bonding. There's your bonding molecular orbital. Okay. And here's your anti-bonding, or the non-bonding, anti-bonding molecular orbitals. So these represent locations in which the electrons can occupy when they're part of this molecule right here. Okay, so we're trying to find if this molecule exists. Okay? So with that said, then you can imagine 2 electrons will occupy the bonding molecular orbital. And remember, the molecular orbitals behave in much the same way as the atomic orbitals behave. And that is, you can only fit a maximum of 2 electrons into this space here. And so that doesn't account for the last electron of this hydrogen ion. So that last electron must move into the next hydrogen. Remember with the Aufbau principle, when we use the Aufbau principle to figure out electron configurations for atoms, well, you apply that Aufbau principle to molecular orbitals for as well, and the formation, the electron configurations for molecules. Okay? And so with that said, then, if we want to write out the electron configuration for the hydrogen ion, then we would have then, if we remember how the symbols that we use for this one, this would be then sigma 1s 2, okay, and sigma 1s, sigma star 1s, and that would be 1, 1. Okay, so you would have an electron then occupying this anti-bonding molecule here. Okay, so that's your electron configuration for this molecule. Okay, and so with that said, this is not a favorable situation. This is something that cannot work. And so with that said, that's already one reason why this cannot work. You have an electron in a higher energy state here. That electron does not like to be there. Now understand this. Okay, understand this. That anti-bonding molecular orbital can be used to form bonds for molecules that are in the transition state. We talked about, remember when we went back, going back to our discussion of kinetics, we have then a molecule that forms that is a high energy molecule that represents a transition state that allows us to move from a low to high energy back down to low again. So this anti-bonding molecular orbital here can be used to form those high energy but very unstable transition states. So this is, if this does occur, this is a very unstable high energy molecule here. Okay, and so this is already working against this molecule here, okay? As opposed to the hydrogen molecule here, which is neutral H2. We don't have to worry about an electron in the anti-bonding molecular orbital there. Okay, and so we're going to see in just a moment then that the bond between, and I want to write this down for you, the bond between hydrogen here, the H2, versus the bond between H2 minus, the bond here is going to be the bond here is going to be weaker than the bond here. So how then do we determine bond energies and where can I say that? Okay, well, we can calculate for what is called the bond order. Okay, we can calculate for what's called the bond order. And that bond order will help us to establish energies to see then that this bond here is going to be a stronger bond than that one. Okay, so let's go ahead then. I'm running a little low on time, so I want to go ahead and I want to talk about, introduce this concept of bond order to you, and I want to practice a little bit, and then I want to continue. Okay, So when we talk about bond orders, basically it's a calculation that we do. Calculation that we do that allows us to compare the bonding situation between different molecules. Okay? And the calculation ends up being very simple. The calculation is a very straightforward, simple one where you take then the number of bonding electrons, okay, and you subtract from it the number of antibonding electrons. And you get this information, and this information from taking the molecule, and we're going to practice this. Taking the molecule and then doing exactly what we did on the previous slide, where we determined then how many electrons will be contributed by each side, by each atom, and then finding out where they fit in the energetic scheme of the molecular orbitals, either how many will go into bonding, how many will go into antibonding. But that's where you get these two numbers from. So you got to draw, you got to be able to do that, and we will talk about that in just a moment. Okay? And then you go ahead and divide it by 2. Okay? And so that means then, if a molecule has a larger bond order, it's going to have a greater bond strength. So the larger the bond order, the larger this number, the greater the bond strength is going to be. Okay? And so make sure you keep that in mind as we go forward with that. Okay? Now, dividing by 2, essentially we're using then this idea with the localized electron model and with the Lewis dot structures. There's only 2 electrons that are shared between 2 atoms in a single bond. Okay? All right, let's go ahead then. And let's do an example. We said then we used hydrogen and hydrogen ion, the hydrogen molecule in its ionic state. Okay. All right. So with this said, then let's go ahead and do this here. So bond order. So remember, in order to calculate the bond order, let's go ahead and do this. In order to do the bond order, we need to identify the number of bonding, the number of electrons in the number of bonding electrons, and the number of anti-bonding electrons. Okay. And how do we find that? Well, remember, we drew this structure here. We did this for hydrogen. And we're going to do this for hydrogen now. Okay. This is for the hydrogen molecule. We're going to define the bond order for hydrogen molecule. Okay. So the bond order. Okay. And so the number of bonding electrons, here it is. So when the 2 electrons here get together, 2 of them fall into the bonding. Remember, this is the bonding interaction. So these are the bonding electrons. These will then be the anti-bonding electrons, or non-bonding. Okay. So when 2 hydrogen atoms get together, the 2 electrons fall into the bonding state. So the number of bonding electrons will be 2. And if you notice here with the anti-bonding interaction, there are 0 anti-bonding molecular orbitals. And so therefore, if we take a look at how we calculate for the bond order, if you take a look at this then, here is the number of bonding electrons. So there's our bonding electrons. There are anti-bonding electrons. We divide it by 2. So the bond order here is going to be 1. Okay. So the bond order for hydrogen is going to be 1. We see that. So keep in mind what we have here. Remember this one. And then let's go ahead and let's take a look at, let's do the same thing for the hydrogen ion. Okay. All right, so here we have the hydrogen ion. Let's go ahead then. Let's do the same thing. We're going to find then the bond order. Okay. The bond order for this molecule here. So we need to identify the number of bonding electrons. Okay. The number of anti-bonding electrons. Okay. So let's go ahead and take a look at this. Okay. Now, do you have to draw this schematic here? No, you don't. As long as you remember then that when you have these atoms coming together, and they combine together to 1s, you'll always obtain a sigma bonding and a sigma anti-bonding. You remember that, and then you just have to make sure you you then place the electrons here. And here's 3 into those molecular orbitals. Then you should be fine. Okay, so 2 electrons will fall into the low energy state, so we have 2 bonding molecular orbitals. And now, because 2 is the maximum number that can fit into this particular molecular orbital, the 1 electron then moves up into the anti-bonding. So therefore, we have 1 anti-bonding molecular orbital. And so if we were to calculate then for the bond order for this, then you see then that here is your bonding, there's your bonding, there's your anti-bonding. Okay. And so therefore the bond order here then is going to be 1/2. The bond order there is going to be 1/2. And so let's compare bond orders here. Okay. So the bond order, let's go ahead and let's take a look at this here. The bond order for H2, remember, was 2. Okay, the bond order for H2 is H2. The bond order, I'm sorry, 1. Sorry. The bond order for hydrogen was 1. 1. Okay. All right. So with that said, then, if you notice here, based on the bond order itself, this bond then, the bond between those two atoms versus the bond between those two atoms, okay, I'm sorry, those two atoms will be almost 2 times as large. So this is 2 times larger, okay? So here is the bond order, and we'll call this BO equal to 1. The BO here is equal to 1/2. The bond order for this is about 2 times larger than the bond order here. We can say then that the strength of this bond here, and let's go ahead and write that down. The strength of this bond here versus the strength of that bond right there. Okay, so we are comparing bond strength when we look at the bond order. Okay, and the bond strength for the hydrogen ion is about 2 times larger than the bond strength that, for the hydrogen ion. Okay, and so that's what we can use bond order for. So bond order, folks, is just basically again, an accounting method that we can use in order to determine then the strength of the bond and thus whether the bond will exist or not. So there are 2 things working against the hydrogen molecule here. Okay, there's 2 things working against the hydrogen molecule and the formation of that. And then first of all, the first factor working against this bond actually forming is that you have 1 electron in a anti-bonding orbital. The second then is the bond order is small. Okay, so basically mean then the bond is weak. It has an electron in the anti-bonding state. So these 2 factors here leads us then to conclude that this molecule does not form. Okay, and so that's how we go about using molecular orbitals. That's how we go about using bond orders in order to determine then whether a molecule can form or not. So what I would like us to do, apply what we know here. Okay, let's go ahead and apply what we have here to determine then whether, and this is what we want to be able to do using this. Okay, I'm sorry, so there it is. Okay, the confirmation the hydrogen molecule has a stronger bond than the ion itself. Okay. All right, so what I'd like us to do then, just to round out here, and I'll pick this up tomorrow on Monday. Again, I promised you I wouldn't assign any of this for your homework, okay? But what I'd like you to do, just try this, okay, and have it ready for tomorrow. Determine whether this molecule exists, okay? The question is, does a diatomic molecule of helium exist, and can it exist based upon the location of the electrons and also in terms of bond energies, okay? So go ahead and just draw out the structure there. Okay, draw out the structure. Draw out the electron configuration for this particular molecule, and then tell me whether this molecule can actually exist or not. Okay. All right. So we'll pick up with this discussion tomorrow, and we'll talk about whether, and I'll answer that question for you about whether we'll go over together and answer the question whether this molecule here can actually exist. Okay. All right. Very good, folks. I will see you tomorrow. Okay. Have a good day.